Every time I get lazy and refer to AI models as open source, I will always get yelled at in the comments saying that they are not open source at all. And they are not wrong. In fact, there's actually not a single fully open source LLM that exists while being near state-of-the-art level. Because in order to be fully open, everything including the model weights and the training data needs to be available. And the only one I can think of being completely open source is the Pythia series from Eleuther AI. And that is like years ago. So when literally everything ranging from model architecture to training pipeline being pretty much made fully public, training data is probably the last and also the second most expensive mode right behind GPUs that define a top-tier AI lab. Just to give you some context of how important training data is, Anthropic is recently exposed of buying millions of physical books and tearing them up to scan the content to use for training data, which just shows how precious training data really is, that a top AI lab is willing to do such a thing that feels really illegal. They won the court case, by the way. On top of that, the meticulously engineered synthetic data used for training are also something extremely valuable. So there is a reason why OpenAI has to obfuscate their chain of thought, because if people get their hands on it, it'll be really easy to make a knockoff clone through distillation. Then with all the stakes on the line, in today's video, let us take a look from a very interesting perspective. To what extent can we reverse engineer training data with the current research? And before we dive into it, if you're tired of shipping apps on platforms that have multi-plan seat limits and surprise bills, there's actually a really clean platform you should know about called Savala from Kinsta. With Savala, you can deploy and host your application, storage, and databases with no friction and completely forget about complexity. Under the hood, Savala runs on Google Kubernetes engine across 25 regions for serious reliability and performance, and your static sites would have Cloudflare's 260 plus edge for global speed and security. But of course, the highlight is that the pricing is not some cheap FNAF jump scare. No fixed plans or feature gates, no seat-based tags, free internal traffic between components with unlimited collaborators, resources, and parallel builds, plus unlimited database usage without role or query caps. So from concept to production, everything can just live in one place. Application hosting on K8s with effortless scaling, S3 compatible object storage that's unlimited and secure, managed databases which you don't have to babysit, and free and lightning fast static site hosting at the edge. You can also bring any workload with public private Git, Docker files, and private images, then move fast with instant preview apps on every PR. And they were also pretty thoughtful about the dev experience. The developer-centric UX of Render or Railway, the global reach of Fly.io, the edge capabilities of Vercel, and Platform.sh style managed services. It comes with real human support and enterprise-grade security. They can even handle the boring stuff like SSL renewals, resource provisioning, storage scaling, and DDoS mitigation. So give Savala a try today, and you can also get $50 in free credits that will be auto-applied if you use the link down in the description, and thank you Savala for sponsoring this video. Anyways, there are multiple ways to have the model spill the beans. When you view the LLM as a statistical machine, you can theoretically infer the data's higher level attributes just by sampling the results empirically. If you view it as a mechanistic circuit, you can poke at individual components and stress test it until it breaks, or if you view it as a deep learning model, then you can theoretically pick data that recreates the gradients direction that will get you towards the target model. But of course, all three of them require different levels of access to the models. And the third way is probably the most concerning one for current AI labs, but let's start with the first one. You technically only need the model API and can treat the model as a black box, but the problem is that this method alone can only leak distributional information as it is not capable of reconstructing the exact details. So in this paper called Can We Infer Confidential Properties of Training Data from LLMs, they proposed prop infer, which gave us a concrete demo of what a pure sampling pathway can and cannot do. So to simulate a model that contains sensitive information, they fine-tuned an open weights model with some medical data called Chat Doctor and created an endpoint out of that. The result is pretty expected. With only the inference endpoint, they were able to estimate the meta statistics of the confidential datasets like the prevalence of HIV or the ratio of female patients. All you need to do is to write prompts about a topic you're interested in, generate a few hundred answers, label each output, and you can treat them as noisy samples from the training distribution, and then reason backwards, as this is basically a maximum likelihood estimator for the true ratio. While this method is basically guessing from a black box using statistics, and you may not recover any singular data, you can still expose business level sensitive statistics about the underlying population for things like medical AI, or the ratio of programming languages used to train a model. But of course, this is not as severe because it doesn't really have that much damage. So let's move on to the next paper by Google called Interpreting the Repeated Tokens Phenomenon in LLMs. This paper shows a very different way of leaking the pre-training data, which is basically exploiting the model rather than aggregating the statistics. The authors first noticed that if you give several models a long string of the same token, the generation suddenly goes crazy. So after 20 or 30 identical characters, the perplexity complexity, which is a score that reflects how surprised the language model is by the next word, collapses. This means the model is overconfident for the wrong reasons and starts emitting memorized artifacts, which sometimes makes the model throws out entire passages straight from its pre-training data. And when you have access to the weights, you can see why. So a small set of attention heads will always direct its query back to position 0, which is the beginning of sequence token, forming something called attention sync if you remember from my old video. In normal usage, the sync contributes only a tiny bit, but when every input key vector is almost identical, the softmax scores would then flatten, the BOS focused attention heads would dominate, and its stored content would overwhelm the weak signal from the repeated tokens themselves. The model therefore starts sampling from whatever those heads memorized during pre-training. For example, if you give Pythia 12b an input that repeats the word as 50 times, the model would just output a rephrased paragraph from a website that appears in the training data. However, the string that the model spits out is not completely random. It is actually dictated by whatever the nearest text the sync head stored as a completion for that exact repeated token context during pre-training. Since you do not know the training data, you cannot pinpoint to a specific secret sentence and demand that to appear, but what you can do is to push the odds. So basically, you can narrow down to a specific topic, and when you give it the right hint, you can increase the chance of the output being in a particular field. If you want code, you can add define or class. If you want academic essays, you can add hashtag abstract, and if you want sensitive documents, hitting it with the copyright could also work. It's just that you cannot deterministically extract a specific string or information, which makes this leakage only semi-controllable. But what you could do is to have it complete hundreds of various prompts and scrape whatever the output data it generates, as it'll technically be memorized information from the model, which is basically the training data. However, the vulnerability is pretty easy to fix. You either just train the model on some synthetic repeated token example so the bias never gets too extreme, or downscaling the sync heads. Then this can be completely avoided. So even though this exploit sounds cool, it is still actually pretty useless when you can just train the model to avoid that edge case. But the last one might actually be unavoidable no matter how hard you train. So right now, with the current topic being reverse engineering the training data, what if we instead change our perspective and skip digging out the training data from a model into simulating the effect of the original training data? In this paper called Approximating Language Model Training Data from Weights, it shows that a model's two weight files, the one before fine-tuning and the one after, would contain strong clues about the private training data used. But of course, that means you need both the base model and the fine-tuned model in order to infer the training data. However, for models like DeepSeek and the Quinn series, they actually do release both versions, so it is possible to test it on them. So how it works is that since fine-tuning basically shifts the parameters by a small amount in every step, with the shift being the sum of all the training examples, the researchers then propose something called select, which turns this observation into an extraction recipe. How you can do that is first, assemble a large public data such as Wikipedia and Common Crawl. Second, for every sentence in that dataset, you would run a single forward and backward pass on the base checkpoint. The backward pass will give a gradient which pushes the parameter a tiny bit, and it will also tell you which way the base model weights would move if you train on that one sentence. Then you do this for every sentence and store each of those gradient vectors. For the third step, compute the full weight difference between the base and the fine-tuned model, as this is the real shift in the parameters which you would want to make with your own data. Then you rank all the stored sentence gradients by how well they point in the same direction as the real shift, and take the top ranked sentences. So when you apply those sentences to the base model, it would partially push the weights toward how the fine-tuned model looks like. And in the last step, set the chosen sentences aside and repeat the ranking step on what is left. So each new batch of sentences pushes the checkpoint further along the straight line, shrinking the gap between its own performance and the fine-tuned model. And you can stop once the sentences would not change the model behavior anymore. This final collection of sentences would then be the public corpus subset, which when used for training, it would approximate the effectiveness of the private data. While the data recovery is only as good as the public data, for instance, if the secret dataset contains data that never exists online, then select would never be able to obtain them. But even so, using select, the authors recovered roughly 90% of full data performance by selecting the right samples that will simulate the unknown training data with a lexical overlap of up to 85% by their vocabulary containment metric. Compared to the other toy-like data extraction research, this research actually gives usable data that the model can train on, which may be concerning for some AI labs. While the mitigation does exist, they are still not as straightforward or might just impact the training efficiency of the model, because you would have to either make your training run mix in more sources of private data or just obfuscate the weights when releasing them, like going through quantization or etc. And honestly, this is quite a lose-lose situation for everyone. Plus, if any many AI labs refuse to open source models anymore because of this, that would suck, as this paper is probably the biggest threat yet to companies' mode, where it can potentially simulate their private training data.
However, I do think none of these would really create a dent in the current landscape of AI models, especially the privatized ones, as the data reverse engineered are still limited to what you can actually apply to, and how state-of-the-art models now all require special complex datasets for things like agentic applications. Reverse engineering may just be a fun experimental research than a threat to top AI companies.
But yeah, what do you think? Let me know down in the comments. And if you enjoyed today's collection of papers and want to learn more, you should check out findmypapers.ai, and you can discover more similar research on there. Or if you're interested in the latest AI research papers, you should definitely check out my newsletter where I cover them weekly. On it, you would be updated on the latest and the juiciest cutting edge AI knowledge that I might not have the time to cover in videos. So if that's your cup of tea, you should go sign up now. And thank you guys for watching. A big shout out to Andrulas Chelius, Chris Ledoux, Deegan, News Research, Kanan, Robert Zaviasa, Louis Muck, Ben Shaner, Marcelo Ferraria, Zane Sheep, Poof and Inu, DX Research Group, and many others that support me through Patreon or YouTube. Follow me on Twitter if you haven't, and I'll see y'all in the next one.